Hello everyone. Today we'll study what is probability. So this lecture is about introduction to probability. Now why do we need to study probability? Now statistics is a science of studying uncertainty about everything. There are many sciences, but statistics is different than other sciences in that it doesn't have fixed conclusions. Basically, it deals with events which are random, which we are not sure about. So, for example, we don't know whether there will be rain or not today. So, such kind of things can be studied only using statistics. And that's why this is a science of studying events and their probabilities. So, today we'll see some of the basic principles regarding probability. Here is an outline of the lecture. We'll first define what is probability, then we'll have some basic principles, we'll have a few examples and study different properties of probability. So basically we know probability is a chance, so we'll see how we can mathematically define this chance, and then how can the chance be computed in various types of situations. Next thing is studying types of events. So how two events are related to each other, do they affect each other, and so on. And after that we'll study a famous formula, Bayes formula, which has plenty of applications in various fields today. So now let's start from the basics of probability. So what is probability? Every day we generally discuss things like, okay, so what are the chances that there will be rain today? For example, in rainy season, if I want to go on some outing, then I need to decide whether I should carry my umbrella with me or not. So for deciding that, what I do is, I look at the sky, see, okay, is there a clear sky or are there some clouds? If there are clouds, then I think that, okay, there are chances that there will be rain today, so I need to take my umbrella with me. Whereas if the sky is clear, then in that situation, what we think is, okay, sky seems to be clear, so most probably there won't be any rain. So this conclusion of ours, whether there will be rain or most probably there won't be a rain, this is nothing but finding probability or chances of some event, and here that event is the rain. Next example is whether there will be drought this year or not. Last year suppose there was a drought, then what are the chances that this year also there will be insufficient rain and there will be drought? Now this is again a random event. We don't know how much rainfall will be there. So we have to just estimate it on the basis of our previous knowledge. So this is again an event in whose probability we are interested. And one more thing is, suppose we have something about some small sample, then can we generalize it to a bigger population? For example, if we again go back to the rainfall thing, then I cannot record rainfall at each and every geological location in a city or in a country. There are some weather stations which record the rainfall. So for example, I want to collect data on say 5 cities, then there might be only one weather station in each city. So on the basis of rainfall at the 5 points, I need to talk about the large area covering all these 5 cities. So in such situation, whatever conclusion I draw on the basis of these 5 weather stations, will it be applicable directly to the all cities, or do I need to make some modifications? So these kinds of things require knowledge about probability. So let's go to the mathematical notations which are needed for defining and computing probabilities. So here S is a sample space. Now what is sample space? Sample space is basically a set which collects all the outcomes of an experiment. Now what is an experiment? Whenever we are in statistics, generally experiment is a thing whose outcome we don't know surely, but we know the possible outcomes. The most common example would be coin toss. Suppose I toss a coin, then before tossing I don't know whether head is going to be there or tail is going to be there, but I surely know that either head or tail is going to be there. So I know all the possible outcomes, but I don't know which one of them is going to occur. So this S, sample space, is a collection of all such possible outcomes. Then next we define a subset of this sample space. Because sample space is a set, we have its subset, which is called as event. So for example, A is some event. So basically this set A is a subset of my original set S. So in the coin tossing thing, A can be say occurrence of head. And then what we are interested in is the chances of occurrence of this event A. So we want to compute P of A, which is probability of occurrence of an event A. Now how do we compute this probability? So for that we need to see what are the possible outcomes, and of them how many are favorable to my event A. So assuming that all the outcomes are equally likely, we define P of A as n of A upon n. And where what is n of A? N of A is the number of outcomes which are favorable to A, and capital N is the total number of outcomes, means it is the cardinality or total number of points in the set S, which is my sample space. This gives me the formula for probability that P of A is n of A upon n. Here is a small illustration. So our basic experiment is tossing a single coin. So suppose we toss a coin, then sample space S is H, T. So either there is going to be a head or there is going to be a tail. And suppose my event of interest is occurrence of head. So the subset that I define is A, which is singleton set H. Now what is n of A? What are the number of sample points, that is elements of S, which are favorable to A? Now there are in all two sample points H and T, out of which only H is favorable to A. So my n of A is 1 and capital N is 2, H and T. So the probability of A becomes half, n of A upon A. Thus we have computed probability of A using the formula number of cases favorable to A upon total number of points in the sample space. Here is second illustration. Now what we do is we move to a next step. Let's have a slightly larger sample space. So suppose we are tossing 2 coins. Now if I toss 2 coins, then what are the possible outcomes? Either both will be heads, or one is head, another is tail, or first one is tail, another is head, or both will be tails. So my sample space consists of these 4 elements, HH, HT, TH and TT. And now the event whose probability I want to compute is B, and it is occurrence of at least one head. So what are the chances that if I toss 2 coins, at least one of them will be a head? So for that I need to first see which are the sample points favorable to B. So let's enlist those sample points. So my set B would be HH, because if there are both heads, it means there is one head at least, then HT and TH. So my B set consists of 3 elements from the original sample space S. So n of B, that is number of cases favorable to B, are 3, and hence my probability of B would be 3 upon 4. So it's exactly 75%. So in this case my occurrence of B has 75% chances. Let's have one more example of the similar type. So suppose we are throwing a die. So the die is 6 faced, and assuming that it is not loaded, there will be 6 equally likely outcomes. So either 1 turns up or 2 turns up and so on. we have up to 6. So my sample space S consists of 6 points, 1, 2, 3 up to 6. And now suppose the event whose probability I want to compute is occurrence of an even number. So what are the chances that when I throw a die, I will get an even number? So this is my event C. Now again going to first principles, what we would do is, we would enlist cases favorable to C. So what are the cases favorable to C? Either I should get 2, or I should get 4 or 6. So these three things are favorable to the event C. So my C set consists of 3 points, 2, 4 and 6. And hence probability of C is going to be 3 upon 6, which is again half. So in general, we can compute probabilities of many such events. So here are few more examples. Suppose if my experiment is tossing 3 coins, then I might be interested in computing probability of getting exactly 2 heads. Or another experiment can be, say, throwing a die again, but now I want to get a multiple of 3. Now multiple of 3 means, in this case, my set of interest would be only 3 or 6. So the probability would turn out to be 2 by 6, which is 1 by 3. Then suppose we may throw 2 dice and we are interested in seeing what are the chances that sum of the outcomes on both the die is greater than 8. Now when we throw 2 dice, then the sample space S would have 36 elements, because there are 6 possible outcomes for first die and 6 outcomes for second die. So total number of pairs would be 6 into 6, that is 36. And out of them, how many would be greater than 8? So for example, if I have 6 on the first die and 3 on the second die, then my sum is 9. So this is the sample point which is favorable to my event of interest. So in such a way, we can enlist all the possible outcomes and then again compute probability of the event. Now, what are properties of probability? So basically, we know probability is nothing but a chance. So when we talk of chances, we never say that the chances are negative. Chances of something can be 0 at most, but they can't be negative. So similarly, probability has to be always greater than or equal to 0. So this is the first property, that probability of any event A is always greater than or equal to 0. It can never be negative. Now second thing is, if we are very much sure about something, what we say is, there are 100% chances that the thing will happen. We don't say that there are 105% or 200% chances and so on. So probability is at most 1. If an event is a certain event or a sure event, its probability is 1. So probability has to be always between 0 and 1. For an impossible event, probability would be 0. Whereas for certain event, probability would be 1. For example, if we are throwing a die, then we can never get 7. If we are throwing a single die, then my outcome has to be between 1 to 6. So if I define my event as getting a 7, then probability of that event will be 0, because it is an impossible event. Similarly, if I define my event as getting an outcome less than or equal to 6 and greater than or equal to 1, then in such case, probability would be 1, because I am always going to get things between 1 and 6. So this is an example of a sure event, or which is known as certain event. Next thing is monotonicity of probability. So if I know that one event is subset of another event, then probability of that event is less than or equal to probability of its superset event. So if A is subset of B, then probability of A is less than or equal to probability of B. So this also has a pretty intuitive explanation. If A is a subset of B, means number of cases which are favorable to A is obviously going to be smaller than number of cases favorable to B. And therefore, in that formula for probability, numerator for probability of A is smaller than numerator for probability of B, and denominator is same in both the cases. So probability of A is less than or equal to probability of B. Then next important property is probability of an entire sample space S. If I compute probability of entire sample space S, then by formula it would be number of cases favorable to S upon total number of cases. But then total number of cases is nothing but number of cases in S. So I have same numerator and denominator. So probability of S is 1. So S, or the entire sample space, if we consider as an event, it is always a sure event or a certain event. And the last property is probability of phi, or an empty set, is 0. Because we know empty set means a set having no elements. So number of outcomes lying in phi is 0, and so the probability of an empty set is 0. So these are the basic properties of probability, using which we will study few more properties. Now for that, let's define different types of event. First of them is a complement. Now what is a complement? Complement is basically not happening. So if I write A complement, then A complement is same as not happening of A. You can see the diagram here. If my S, a sample space, is denoted by rectangle and my A is the circle, so A is the event, then the shaded portion is not happening of A. So shaded portion is A complement. And then how do we compute probability of this A complement? So here is the formula for the same. Probability of A complement is 1 minus probability of A. Now how do we get this? Total probability of my entire sample space is 1. That we know from the basic. And as you can see here, for getting A complement, I need to subtract the set A from the entire set S. So probability of A complement is 1 minus probability of A. And let's have an example. If suppose I am again in that throwing of die experiment and I define my event A as getting even number, then my A is having elements 2 or 4 or 6, and its complement would become getting an odd number, so it is either 1, 3 or 5. So here we have probability of A as half and probability of A complement is 1 minus half, so it is also half. Next type of event that we are going to define is union. Now what is union? Union is basically occurrence of either of the events or both the events. So suppose I have two events A and B, then union of AB is occurrence of either A or B or both. So in the Venn diagram you can see the entire blue portion is A union B. So suppose we define A as getting a multiple of 2 when we throw a die. Then my set A would be 2, 4 and 6. And then we define event B as getting a multiple of say 3. Now multiple of 3 we know are only 3 and 6. So union of these two events would be union of these two sets. So it would be 2, 3, 4 and 6. So my A union B consists of 4 elements. Next type of event is intersection. Now what is intersection? Intersection is basically simultaneous occurrence of two events. So if I have two events A and B represented by circles, then their common portion, which is shaded here, denotes intersection. So, intersection means that both the things are happening together. So again, if I have same A and B, if my A is getting a multiple of 2, which is 2, 4, 6, and B is getting a multiple of 3, say 3 and 6, then the sample point which is common to both of them is only 6. So my A intersection B would be singleton set 6. Now that we have defined these various types of events, let's compute the probabilities of such events. So first thing is probability of union. How to compute probability of a union if I know probabilities of individual events? Now this is known as addition rule. So I want to compute probability of A union B. Now you can see from the diagram, if I simply add both the probabilities, then there is some common region which would be added twice. So I need to do something about that common region. So if I add, then it's coming twice. So I need to subtract it once so that repetition is eliminated. And so probability of A union B is probability of A plus probability of B minus probability of A intersection B. So for knowing the probability of union, we need to know probability of set A, probability of set B, as well as the probability of their intersection. If we know these three things, then only we can compute probability of their union. Next, suppose we want to generalize this formula to 3 events. Now we have 3 events A, B and C, and we want to compute probability of their union. Means probability that at least one of them will occur. So here also, if we first add 3 things, then the common portions would be repeated. So we need to subtract common portions. Now there will be some portions which will be common to 2 events, and there will be some portions which will be common to all the 3 events. So first, let's subtract those portions which are common to 2 events. So we are subtracting probability of A intersection B, probability of B intersection C, and probability of A intersection C. But then the thing is, the portion which was common to all the 3 would be again subtracted twice. So we need to add it once. So we would add this last term, probability of A intersection B intersection C. So here is the final formula. So we first add individual probabilities, then subtract the probability of intersection of two events, and then add the probability of intersection of all the 3 events. This gives me probability of A union B union C. Next, let's define another type of event, which are known as mutually exclusive events or disjoint events. Now what do I mean by mutually exclusive? Mutually exclusive means occurrence of one event would prevent other event from happening. So occurrence of one excludes the occurrence of other. Hence they are known as mutually exclusive. And therefore they cannot occur simultaneously. They cannot occur simultaneously means if I try to see what is the common region, then that common region would be an empty set. So A intersection B is an empty set phi. As you can see in the diagram, my A and B are totally distinct. There is no common portion. For example, I can define A as getting an odd number and B as getting an even number. Then it can never happen that I am getting odd number as well as even number. So A and B are mutually exclusive events or disjoint events. And we can also see from the sets that A set is 1, 3, 5, B set is 2, 4, 6. So their intersection, you don't have anything. So intersection is an empty set, and hence probability of this intersection is 0. So this A intersection B becomes an impossible event if my A and B are mutually exclusive events. Next thing is what is known as independent events. Now what are independent events? Independent event means outcome of one event does not depend on the outcome of other event. So, for example, I define A as getting head in the first toss of a coin and B as getting head in the second toss of a coin. Now, when I toss a coin once, I get either head or tail. Then when I am going to toss the coin at the second time, even though I know the previous outcome, I cannot say anything about the next outcome. Even if suppose head had come on the previous toss, still I can't say guaranteedly whether I'll get head or tail or similar. So these things are known as independent events. In case of independent events, probability of A intersection B is probability of A into probability of B. So this is a product rule that if two events are independent, then probability of their intersection can be computed by taking product of their individual probabilities. Now one more point to be noticed is mutually exclusive events, if they have non-zero probabilities, then they cannot be independent. Because as we saw that mutually exclusive events basically mean that happening of one event prevents the happening of other. So it means that happening of the second event depends on happening of the first event, so they can never be independent. And mathematically also this can be proved using this formula for probabilities of independent events. But then in real life things may not be independent. So we need to have some method to study what is known as non-independent events. If two events depend on one another, then we need to do something. For example, here we have one such setup where probability of outcome of one event changes depending on outcome of some other event. Let's define the two events. Suppose my event A is getting a red ball in the first draw. Now you can see the box here. So there are 4 red balls and 2 blue balls. So I am interested in two events. My event A is getting a red ball in the first draw. I draw the ball, I keep it aside, and then I draw the ball second time. So B is event getting a red ball in the second draw. Now let's first compute probability of A. Now what is probability of A? Out of 6 balls, 4 are red balls. So chances of getting a red ball are 4 by 6. So probability of A is 4 by 6. Now for computing probability of B, I need to know whether my first ball drawn was red or blue. So suppose let's assume that the first draw drawn was red. Now the situation would be as in the second box. Out of 4 red balls, 1 is already drawn, so I'll be left with 3 red balls and 2 blue balls. So now probability of getting a red ball in the second draw would be 3 upon 5. So this is denoted by writing probability of B given A. So given that A has already happened, given that I had obtained a red ball in the first draw, what are the chances that I'll get red ball in the second draw? So those chances are 3 upon 5. Now what would have happened if I had got blue ball in the first draw? Here is the situation. If I had got blue ball in the first draw, then at the time of second draw, just before the second draw, my box position would be as in second picture. I would have 4 red balls and I would have 1 blue ball. So in such situation, probability of getting a red ball in the second draw would be 4 upon 5. So this is probability of getting a red ball given the fact that in the first draw I had got blue ball. So this is probability of B given A complement, and it is 4 by 5. And we can see that probability of B given A was 3 by 5, whereas probability of B given A complement is 4 by 5. Means, depending on whether A has happened or A has not happened, probability of B changes. So we can say that events A and B depend on each other. Now in such situations, how do we compute the probability of intersection? We know that if two events are independent, then the probability of their intersection can be computed by simply taking their product. But what would happen if they are not independent? So here is the multiplicative rule for non-independent or dependent events. Here you can compute probability of A intersection B as probability of A into probability of B given A, and this probability of B given A portion is known as conditional probability of B given that A has already occurred or happened. And same thing can be written in the reverse way by replacing A and B. So it would be probability of B into probability of A given B. Thus, probability of intersection of A and B can be computed using marginal probability of one event and conditional probability of another event. Using this fact, we are going to have something known as Bayes rule or Bayes formula. So before that, we need to define partition of the sample space. Now what is a partition? Suppose my sample space is S, and then I divide this sample space into distinct parts. Distinct part means they are separate parts, they don't have anything in common. And if I take all those parts, then combinedly they make up my entire sample space S. So my S can be written as union of these sets B1, B2 up to say Bk, and these Bk's are distinct or disjoint, means Bi intersection Bj is phi if I is not equal to j. And one more thing that we assume is probability of Bi is not 0 for any I. Means that none of these Bi's are impossible. All of them have some non-zero probability. Now in such cases, probability of any event A can be computed using probabilities of this disjoint sets. So this event A, now we can see from the first line here that S is B1 union B2 union up to Bk. So basically S is union of all Bi's. So event A can be written as A intersected with S, because S is the entire sample space. So it would become A intersected with this union of Bi's, and now because it is A intersected with union Bi's, I can take the union common. So it would be union of the sets A intersection Bi, where union is over all the i's from 1 to k. And we know that these Bi's are disjoint, so the events A intersection Bi's will also be disjoint, and because of that I can add their probabilities to get the probability of A. So probability of A would be sum over probability of A intersection Bi over all the i's. And then from the multiplicative rule that we established here, probability of A intersection Bi can be written as probability of Bi into probability of A given Bi. So probability of any event A can be factored into small quantities, which is done through the partitioning sets. And then the last formula here is known as Bayes theorem or Bayes rule. So it is useful when I want to compute probability of any set Br given A. So what we do is, probability of Br given A is probability of Br intersection A. So it can be written as probability of Br into probability of A given Br upon this joint thing. So what we have is this final formula. This is also known as turnaround probabilities, because for computing probability of Br given A, we are using probability of A given Bi's. So we are basically turning around the probabilities and computing the things that are of interest to us. Now this Bayes theorem has plenty of applications. Let's study one example for that. So pollution of rivers in the United States has been a problem for many years. So there was some study related to pollution. They had defined 3 events. Event A is the river is polluted. Event B is a sample of water tested detects pollution. Now we have to remember that A and B are not same, because even if there is a pollution, it may not get detected by the sample, by the test that we are using. And then C is fishing is permitted in that river. And some probabilities were known on the basis of prior knowledge. Probability of A means chances that the given river is polluted is 0.3, means 30%. Probability of B given A means given the fact that the river is polluted, what are the chances that the test detects pollution? So those were 75%. So that probability is 0.75. Probability of B given A complement is 0.2. Now what is B given A complement? B is a sample of water tested detects pollution, and A complement means river is not polluted. So even though the river is not polluted, there are 2% chances that we'll get conclusion from our test that the river is polluted. So this is B given A complement. Then probability of C given A intersection B is 0.2. Now what is A intersection B? A intersection B here is simultaneous occurrence of A and B, means the river is polluted and a sample also detects pollution. And in such cases, probability that still the fishing is permitted is 0.2, means 2%. If we already know that the river is polluted and even the test turns out to be positive, then there are only 2% chances that the fishing would be permitted. Probability of C given A complement intersection B means that probability that the fishing is permitted given the fact that the river is not polluted but the test says that there is a pollution are 15%, so 0.15. Similarly, we can define probability of C given A intersection B complement. So it would be event that the river is polluted but the test doesn't detect pollution, and so fishing would be permitted. So it has 80% chances, so probability is 0.8. And probability of C given complement of both A and B is 0.9, means if we know that the river is not polluted and even the test doesn't detect any pollution, then there are 90% chances that fishing would be permitted in that river. So using these, we need to compute probability of these events. So first event is probability of A intersection B intersection C. Now A intersection B intersection C would mean that the river is polluted, the test detects the pollution, and still fishing is permitted. So how do we compute this probability? So A intersection B intersection C probability can be computed by this formula. What we can do is, basically, we do successive conditioning. So first we know probability of A, so it is A into probability of B given A, and then into probability of C given that A and B both have happened. So probability of C given A intersection B. And if these 3 probabilities are known, then we can compute probability of A intersection B intersection C. Similarly, we might be interested in, say, probability of B complement intersection C. Now B complement intersection C would be that the sample tested doesn't show any pollution and fishing is permitted. So we can exactly compute in the similar manner. It would be probability of B complement into probability of C given B complement. Next thing is, say, probability of C. In general, suppose we don't want to worry about pollution and all. In general, given any river, what are the chances that the fishing is permitted? So that would be this probability of C, which is known as marginal probability of C. And one more thing that might be of interest is probability that the river is polluted given that the fishing is permitted and a sample tested did not detect any pollution. This is basically of high interest because it's a serious thing that the river is polluted but the sample didn't detect any pollution, and that's why fishing is permitted. So it may harm people's health. So this can be denoted by probability of A given B complement intersection C. A is probability that the river is polluted given the fact that the test did not detect pollution, so B complement, and C, the fishing is permitted. So this also can be computed similarly using all the previous things. Now let's have one more example of the similar type just to have an idea of how Bayes' rule can be used. So suppose in a certain country 0.3% of the total population has cancer. Then the probability of the doctor correctly diagnosing a person with a cancer as having the disease is 0.78. Means there are 78% chances that the doctor correctly diagnoses the person, and the probability of incorrectly diagnosing a person without cancer as having disease is 0.06. So this is known as false positive, that a person actually doesn't have a cancer but he was incorrectly diagnosed as having cancer. So probability of that here is 0.06 or 6%. Now what are the quantities that are of interest? So here we might be interested in finding probability that a person is diagnosed as having cancer. Means in general I don't know whether I have a cancer or not, but what are the chances that I will be detected positive for cancer? This will be again marginal probability of getting detected positive. And second thing is, what is the probability that a person actually has cancer if he is not diagnosed with cancer? Now this is a very serious thing, because suppose the person is detected negative, then obviously he won't start any medication, but in such cases if he actually has a cancer, it's a serious problem. So we are interested in computing this probability, and we are basically interested in seeing that this probability is kept to the minimum. So let's see the notations for the same. Suppose we define event A, that person has cancer, and then event B as person is diagnosed as having cancer. So the information that is given to us is 0.3% of the total population has cancer. 0.3% means probability would be 0.003. So probability of A, probability that any random person has cancer is 0.003. Next thing that is given to us is correct diagnosis of cancer is 78%. So probability that a person is diagnosed as having cancer given the fact that it has the cancer is probability of B given A is 0.78. Next is probability of false positive. So probability of B, that is the person is being diagnosed with cancer given the fact that he doesn't have a cancer. So given A complement is 0.06. And now using these three quantities, we need to compute what is the probability that a person is diagnosed as having cancer. Means in general, what is marginal probability of B? So probability of B, again we can use that partitioning thing. A and A complement sets can be considered as partitioning sets, because A union A complement is my entire sample space S and A intersection A complement is phi. So probability of B is probability of B given A into probability of A plus probability of B given A complement into probability of A complement. Now from this formula, we know probability of B given A, we know probability of A, we know probability of B given A complement, and probability of A complement would be 1 minus probability of A. So we know everything from the right hand side, and hence we can compute probability of B. Next thing was to compute probability that a person has cancer if he is not diagnosed with cancer. So probability of A given the fact that B didn't happen means probability of A given B complement. So this can be computed as probability of B complement given A into probability of A upon probability of B complement. How do we compute probability of B complement given A? It would be 1 minus probability of B given A. And how do we compute probability of B complement? It would be 1 minus probability of B, which we have computed just now. So in this way, we can see reliability of test using the Bayes formula. So I will today stop here. Thank you.